Hi, I'm Scott Knockley. In this video, we're going to look at modified Denevitt and Hartenberg parameters. So by the end of this video, you should be able to identify the modified Denevitt and Hartenberg parameters for robot manipulators. As well, you should be able to understand how the modified D&H parameters relate to link transformations. In previous videos, we looked at the 6 problems of robot kinematics, and we found the solutions to those 6 problems for the planar case. However, we're interested in spatial robots as well. These are robots that operate in 3D space, so there's translations about the X, Y, and Z axes, as well as rotations about the X, Y, and Z axes. So that's full spatial motion is 6 degrees of freedom. All right, and so these previously developed planar solutions can be difficult to use to solve for the spatial robot case. All right, so there's issues around the representation of the links of the manipulator because we have these rotations in 3D. As well, the derivatives of the rotational kinematics is not as straightforward for the 3D case. So we need a way to represent our 3D manipulators, okay? And we do this by assigning frames to each link of the robot. So we assign coordinate frames that are associated with each link. Now, conventions have evolved over time to describe these spatial links and how we assign these coordinate frames. And Denevitt and Hartenberg demonstrated and defined 4 parameters that allow the description of a spatial link. And these have become known as the Denevitt and Hartenberg parameters, or D&H parameters. In this video, we're going to look at what's called modified D&H parameters. And this is what you'd find in the textbook Introduction to Robotics. All right, so it's a variation of what we could say true D&H parameters. And in subsequent videos, we will also look at true D&H. But for now, we're going to look at the modified D&H parameters. So here we have 2 links of a robot. We have link I minus 1, and we have link I. Okay, there's axes associated with these links. This is axis I minus 1, this is axis I, and this is axis I plus 1. Between 2 successive joint axes, we can define a variable A, which is the common normal distance between 2 axes. All right. Now, in terms of frame assignment, the first thing we do is we assign the ZI axis, so it's pointing along the ith joint axes. So here's ZI, and we draw it along, so it's collinear with axis I of joint I. We next assign XI axis, pointing along the common normal of the joint axes of link I and link I plus 1. So here's the axis of link I, and here's the axis of link I plus 1. This is the common normal, and we assign XI along that axis. And then lastly, we just assign the YI axis to form a right-hand frame, and you see YI here. Often when we draw our robots out, we will just draw the X and Z axes, and we'll omit the Y axis, but you can easily find it, the direction of it, using your right-hand rule. So there are 4 D&H parameters, in this case the 4 modified D&H parameters. The first one is AI minus 1, which is the distance from ZI minus 1 to ZI measured along XI minus 1. All right, so here we have ZI minus 1. Here we have ZI. This is the common normal, all right, which is the axis of XI minus 1. And then you can see here we have AI minus 1. All right, and so that is our first D&H parameter. Our next parameter is alpha I minus 1. And it's the angle between ZI minus 1 and ZI measured about XI minus 1. All right, and so you can see that here. That's alpha I minus 1. And you find the direction of that rotation using your right-hand rule. So you'd put your thumb in the direction of the xi minus 1 axis, And then if it's curling about your thumb, that's a positive rotation. If it's going the other direction, that's a negative rotation. All right, so keep that in mind as you go through assigning your D&H parameters. You really need to understand where it's positive and negative in terms of rotations. All right, so that's our second D&H parameter. Okay, alpha I minus 1. Our next parameter is DI. It is the distance from xi minus 1 to xi measured about zi. All right, so here we have xi minus 1, and here we have xi. And so the distance between these two axes measured along zi is di, which is this variable here. So that's our third parameter. And then our last parameter, theta I, is the angle between xi minus 1 and xi. So again, here's xi minus 1, here's xi, and it's the angle between those measured about zi. All right, so this is theta I. And the same thing again, use your right hand rule. You put your thumb in the direction of the positive axis, and you can tell if it's a positive or negative rotation. Di and theta I would be the joint variables for our robot. So if joint I is a revolute joint, theta I would be a variable that we change. If joint I was a prismatic joint, di would be the variable that we change. And then a I minus 1 and alpha I would often be fixed parameters. But we'll look at that more as we do some examples in subsequent videos. So you may have noticed, though, that the D&H convention doesn't result in a unique attachment of frames to links. So example, one has the freedom to choose the direction of ZI axis along the joint axis I. All right, so in this example here, all right, we've assigned Z2 in this direction on the left here, but we could have also assigned Z2 in this direction. All right, this is the joint axes, so we have a freedom of choice in terms of which direction we want to make positive. If we go back to our other figures here, all right, we chose ZI to be in the up, going up. We could have just as easily assigned ZI going down. In that case, YI would have been coming out of the page. So keep that in mind. There is some freedom of choice there. Okay. That being said, conventions have developed in order to how we should assign our axes. All right. So one thing is we often attach a base frame, frame 0, to the base of the robot. Frame 0 is often referred to as a reference frame. Okay, so it doesn't move. And as a convention, we often assign frame 0 so that it's coincident with frame 1, and that is Z0 axis is along Z1. They're collinear. All right, when joint variable 1 is 0. Okay, so if that's the case, x0 is parallel to x1 when joint variable 1 is 0 as well. Okay, obviously as soon as you start rotating joint 1, there'll be an angle between x0 and x1, but in 0 displacement, they would be parallel to each other. All right, as well, we have some freedom how we assign frame n. So for convenience, if joint n is revolute, we try and choose the direction xn so that it's parallel to xn minus 1 when theta n is equal to 0. Okay, and the origin of frame n is chosen so that where possible we try and make dn equal to 0. All right, so we try and make as many of our D&H parameters 0 as possible because that will make the kinematics simpler, as you'll see later in this video. For joint n prismatic, right, we choose the direction of xn so that theta n is equal to 0, and the origin of frame n is chosen at the intersection of xn minus 1 and joint axis n when dn is equal to 0. So this above conventions is referred to as 0 displacement. So you can think of it as, what does the robot look like if all our joint values are 0? Okay, And we'll often draw our robots out in zero displacement diagram so that we can assign our D and H parameters. And we'll do that in our examples. Now, those 4 D and H parameters, in this case we're looking at the 4 modified ones, correspond to the following homogeneous transform. So we have the homogeneous transform that describes frame I with respect to frame I minus 1. All right, it's equal to a rotation about the xi minus 1 axis by alpha I minus 1. It's then a displacement along the xi minus 1 axis by our ai minus 1 value. We then have a rotation about the zi axis by theta I. And then lastly, we have a translation along the zi axis by di. Again, alpha, a, theta, and d are our 4 D and H parameters. Now, we can swap the order of these two, and we can swap the order of these two. All right, but we can't just swap all of them around. So it doesn't matter if we first do the rotation then displacement about xi minus 1. We can displace it, then rotate it. It doesn't change anything. Likewise, we can do the rotation about zi, then the translation, or we can do the translation and then the rotation. So we can write this out again just to show you. So we could do the displacement first, then the rotation by alpha I minus 1, and then we can do our displacement about the zi, and then we can do our rotation about the zi by theta I. And it's the same answer, all right? Nothing, it doesn't matter, all right? You can switch those two, and you can switch those two. All right, so if you were to multiply this out, all these different translations and rotations, all right, we will show that our transform describing frame I to I minus 1 is equal to the following. And remember, C denotes cosine and S denotes sine, as we use throughout the course. So this is the homogeneous transform based on those D and H parameters. And then we have C alpha I minus 1, 0. All right, so this block here is our rotation part, and then we have our translational part. All right, and so that is our 4x4 homogeneous transform. Okay, and you can see we have our 4 D and H parameters in it. We have theta I, we have alpha I minus 1, we have AI minus 1, and we have DI. All right, so this is an important formula, and we're going to use that throughout the course. So in subsequent videos, we're going to do a number of examples to illustrate the assignment of our link frames and link parameters. It is really important that you understand how to do this correctly, as it forms the foundation for developing the kinematics of our robot manipulators. All right, so getting those D and H parameters correct will allow us to develop a correct forward displacement solution. And as you saw with the planar case, the forward displacement solution is the basis for everything else. All right, we can do our inverse displacement from it. We can get our forward velocity and our Jacobians and so on. So we need to get the parameters correct so that we can do the kinematics correctly. So make sure you understand how to do that by going through all those example videos.